Today we're going to finish our lesson on continuity. Remember, a function f of x is said to be continuous at a if f of a is defined, the limit as x approaches a of f of x exists, and that your function evaluation and your limit are the same finite value. So let's take a look at a different type of example than last time. For what values of c is the function f of x continuous everywhere? Well, x squared minus a number is a polynomial function. Polynomial functions are continuous everywhere, so x squared minus c will be continuous for all values less than 5. 4x plus 2 times a number is a linear function. Linear functions are continuous everywhere, so it's continuous for all values greater than 5. So the only place that this function could be discontinuous is at x equals 5. So what we need to make sure is that this function is defined at 5, that the limit exists, and they give you the same thing. So in order for that to happen, your function evaluation has to give you the same thing as your upper limit and your lower limit. In order for the limit to exist, your upper and lower limits need to match. And in order for this function to be continuous, these limits need to give you the same thing as the function evaluation. Now notice f of 5 would use this bottom piece, as would the limit as x approaches 5 from above. So those are going to be the same value. Direct substitution, plug in x equals 5, we get 4 times 5 plus 2c, or 20 plus 2c. Now for your lower limit, when we plug in the direct substitution 5, we get 5 squared minus c, or 25 minus c. Now in order for this function to be continuous at 5, the upper limit and the lower limit need to match. So we can set that 20 plus 2c equal to that 25 minus c and solve for c. Add c to both sides, subtract 20 from both sides, and we get 3c equals 5, or c equals 5/3. So in order for this function to be continuous everywhere, in other words, meet the conditions of continuity for all values from negative infinity to positive infinity, this c value has to be 5/3. Let's take a look at another one. Here's a piecewise function with 3 pieces, and I want to know for what values of a and b will make this function continuous everywhere. So what do we need to do? Well, the only values we are concerned at are at 3 and 4. So we need to make sure that this function is continuous at 3 and that it's continuous at 4. So we need to find the a and b values that will make that true. Now at x equals 3, my function evaluation, which uses this top piece, will also give me the lower limit. So when I do my direct substitution, I get 3x plus 2, or 5. So now I need my upper limit, which uses this middle piece, to be equal to 5, and that's where 3a plus b equals 5 comes from. Now at x equals 4, I need my function evaluation, which uses this middle piece here, which also gives me my lower limit, which gives me 4a plus b, to be equal to my upper limit, which will use this bottom piece here, which gives me 2, which is where my 4a plus b equals 2 comes from. So based on all of that, we have that 3a plus b equals 5, and 4a plus b equals 2. So I have a system of linear equations. I'm going to solve this equation for b, and solve this equation for b. And so now if I know that b is equal to this, and I know that b is equal to this, well then this must equal this. So now when I solve for a, I get a equals negative 3. So that gives me my value for a. Now I need to know my value for b. Well, I can plug negative 3 into this one, or I can plug in negative 3 to this one. It doesn't matter because they're both the same. So when I do, I get that b equals 14. So that piecewise function will be continuous everywhere if a is equal to negative 3 and b is equal to 14. Now the last thing we're going to talk about that's related to continuity is something called the intermediate value theorem. This is a very important theorem that you need to know. If f of x is a continuous function on the closed interval a to b, and n is any number between f of a and f of b, so between this function evaluation, or y, and this function evaluation, or y, n is any number in between there, so long as f of a is not equal to f of b. If that holds true, if those conditions hold true, then there is a number c in between a and b where the function evaluation at c is equal to n. Sometimes it's easier to look at this graphically. So here's a and here's b. Notice this function is continuous from A to B. There's no removable or non-removable discontinuities. What the intermediate value theorem says is that between f of A and f of B, every y value in between here is accounted for. So for some random value n, there is a point between A and B that gives that to you. Same thing here. Here's A and here's B. Notice my function is continuous from A to B. That means for any value between f of A and f of B, any value at all, there's at least one place between A and B that gives you that y value. This one happens to have 3. So where is the intermediate value theorem useful? It's useful in, say, wanting to find roots. Remember, roots of a function are solutions to where that function is equal to 0 or the x values of the x-intercepts. Well, if I wanted to know that where this function was equal to 0, we could try to factor and set the factors equal to 0. We could try to graph, but sometimes it's really hard to figure out exactly what the x value is that makes that function equal to 0. But notice I don't want to necessarily know what the root is. I just want to know that that root is between 2 and 3. So what I'm trying to prove here is that for some x value, I don't care what the x value is, but for some x value between 2 and 3, f of that x value will give me 0. Well, f of x is a polynomial function, and polynomial functions are continuous everywhere, and so therefore this polynomial function is continuous from 2 to 3. That means that the intermediate value theorem will apply. So let's figure out, we'll call this A and we'll call this B. So let's find what f of A is, which would be f at 2, which is -1, and what f of B is, which B is 3, which gives me 31. Now notice root, which means your function evaluation is 0, is between -1 and 31. So therefore the intermediate value theorem says there must be a number C between 2 and 3 so that f evaluated at C would give you 0, which lies between -1 and 31. So the intermediate value theorem did work. So let me show you this again graphically. As you can see, this would be the ordered pair 2, -1, and this would be the ordered pair 3, 31. So I have these graphed for you here. Now what do you notice? Here's the ordered pair 2, -1. Here's the ordered pair 3, 31. The only way, this is a continuous function, so there's no breaks, no holes, no jumps. The only way to get from this red point to this blue point is to cross the x-axis somewhere between 2 and 3. I don't care where, but it has to happen somewhere between 2 and 3. If it happened over here, well then that would not pass the vertical line test and it wouldn't be a function. But this is a polynomial function. So what the intermediate value theorem is saying is that to get from here to here, we have to cross the x-axis somewhere between 2 and 3. So again, since f of A, which is f of 2, and f of B, which is f of 3, since 0 lies between them, right? 0 is between -1 and 31. By the intermediate value theorem, there must be some C value between 2 and 3 where f of C is equal to 0. That's what the intermediate value theorem says. That's it for this time. I'll see you next time.